we can certainly talk about it in terms of a pi, which is the basic idea for area and polar coordinates. Here's our pi, and here's a slice of the pi. The slice has a piece of arc length on it, which I'm going to call delta theta, and the area of that shaded in slice I'm going to call delta A. And let's suppose that the radius is A, little a. So this is a pi of radius A. That's our picture. Now it's pretty easy to figure out what the area of that slice of pi is. The total area is, of course, pi a squared. We know that. And to get this fraction, delta A, all we have to do is take the percentage of the arc of the total circumference. That's delta theta divided by 2 pi. This is the fraction of area, fraction of the total circumference, the total length around the rim. And then we multiply that by pi a squared, and that's giving us the total area. And if you work that out, that's delta A is equal to the pi's cancel, and we have a half a squared delta theta. All right, so here's the basic formula. And now what we need to do is to talk about a variable pi here. That would be a pi with a kind of a wavy crust, right, which is coming around like this. So r is equal to r of theta. The distance from the center is varying with the place where we are, the angle where we're shooting out. And now I want to subdivide that into little chunks here. Now the idea for adding up the area, the total area of this piece that's swept out, is to break it up into little slices whose areas are almost easy to calculate. Namely, what we're going to do is to take, and I'm going to label it this way. I'm going to take these little circular arcs which go. So I'm going to extend past where this goes, and then I'm going to take each circular arc here. So here's a circular arc, and then here's another circular arc, and here's another circular arc. It's just right on the nose in that case. Now, in these two cases, so basically the picture that I'm trying to draw for you is this. I have some sector, and then I have some circular arc, and maybe it takes a little extra. There's a little extra area. I'm making an error in the area. This is a little extra area. And maybe to draw it the other way, I'm a little short on this one. And let's say on this one I'm right on the nose. I have the same arc as the curve of the surface. All right? Now, this is a little bit like the step functions that we used in Riemann's sums. It's practically the same. Eventually, this little band of stuff that we're missing by, if we take very, very narrow little slices here, is going to be negligible. It'll get closer and closer to the curve itself, so that area will tend to zero in the limit. So we don't have to worry about it. And the approximate relationship is sitting here, where this distance now is r. So this radius is r, and this is this delta theta. And so in the approximate case, what we have is the delta A is approximately 1/2 r squared delta theta, which is practically the same thing we had here, except that r is replacing the constant there. And it's approximately true because r is varying. And then in the limit, we have the exact formula for the differential, which is this one. So this is the main formula for area. And if you like, the total area then is going to be the integral from some starting place to some end place of 1/2 r squared d theta. Now this is only useful in the situation that we're in. Namely, so this is the other important formula, and this is only useful when r is a function of theta. And this is the way in which the region is presented to us.